All right, let's dive into a classic physics problem from the legendary Irodov textbook. Now, this is one of those questions that, on the surface, looks incredibly tough. But as you're about to see, it has a solution that is so surprisingly simple and elegant, it might just change the way you think about gravity. Okay, so picture this. You're floating, right, in the middle of a giant, hollow planet, a perfect sphere. Now, there's mass above you, below you, to your left, to your right, literally all around you. Every single particle of that sphere is pulling on you. So the big question is, what's the final result? Which way do you go? And the answer is nowhere. The net gravitational force on you, no matter where you are inside that shell, is zero. Exactly zero. It would feel like there's no gravity at all. I know, that sounds completely counterintuitive, so let's break down exactly why it's true. So this is problem 1.212 from Irodov's Problems in General Physics. If you've studied physics, you probably know this book. It's famous for really pushing students to think. And this problem, it's a perfect example of why. It forces you to think way beyond just plugging numbers into a formula. Now, our main tool here, really our only tool, is Newton's law of universal gravitation. But here's the catch, and it's a big one. Look at the formula. It's specifically for the force between two point masses, little dots of mass. Our hollow planet, well, it's obviously not a point mass. And this is the first trap that so many of us fall into. We think, okay, I'll just use calculus. You imagine breaking up the shell into an infinite number of tiny point masses, calculating the force vector from every single one, and then trying to sum them all up with some monstrous integral? Honestly, that sounds like a total nightmare. There has to be a smarter way to do this. And there is. The solution isn't about brute force calculation. The real genius here, and in so much of physics, is spotting a shortcut. And for this problem, the shortcut is all about the perfect, beautiful symmetry of the sphere. So here's the game plan. We don't actually need to calculate the total force. What if we can just prove that for any little piece of mass pulling you in one direction, there's a matching piece on the exact opposite side pulling you with the exact same force in the opposite direction? If we can show that's true for the whole sphere, then the net force just has to be zero. Let's actually build this proof visually. Think about it like you're the prize in the middle of a perfect 360-degree tug of war. For every single rope pulling you forward, there's another one pulling you backward with the exact same strength. Let's see how that works with gravity. Okay, here's how we set it up. It's brilliantly simple. From wherever you are inside the shell, let's call your position point A, imagine a thin cone, like a laser pointer beam, that shoots out from your eye in both directions, forward and backward. Where that cone hits the shell, it carves out two little patches of mass. We'll call the small mass of the near patch dm1 and the one on the far side dm2. Now, each of these patches is pulling on you. We'll call those forces F1 and F2. So here's where it gets really interesting. How do the masses of these two patches compare? I mean, it's obvious one is closer and one is further away. Your gut might tell you the closer one has a bigger effect, right? But let's actually look at the mass itself. This is the key. It's all about geometry. You know how a flashlight beam spreads out and gets bigger the farther it shines? Our little cone does the same thing. The area of the patch it creates on the sphere gets bigger with the square of the distance. And since the planet shell is uniform, if the area is bigger, the mass is bigger. So the mass of a patch is proportional to the distance squared. The farther patch is, in fact, more massive. And this is where the magic happens. Let's go back to Newton's law. The force is proportional to the mass divided by the distance squared. But wait a minute. We just showed that the mass is proportional to the distance squared. So you have distance squared in the top of the fraction and distance squared in the bottom. They cancel. The distance squared terms just vanish. They completely cancel out. And what that means is that the pull from the smaller, closer patch is exactly the same strength as the pull from the larger, more distant patch. They're equal in magnitude, and since they're on opposite sides, they pull in exactly opposite directions. A perfect balance. And here's the final piece of the puzzle. That cone we imagined, it was totally arbitrary. We could have pointed it in any direction we wanted. Up, down, sideways, at any angle. For every single tiny piece of that sphere, we can use this method to find its canceling partner on the direct opposite side. The entire sphere can be perfectly paired up into these sets of canceling forces. Every single pull is met by an equal and opposite pull. So when you add it all up, what do you get? A big, fat zero. The net force is zero. And we proved it without writing a single integral. Now you might be thinking, Okay, that's a really neat trick for a textbook problem. But this result is actually a huge deal in classical mechanics. It's one part of a fundamental concept called the shell theorem. See, this idea is what allows us to treat the entire Earth, for our calculations, as if all its mass was squeezed into a single point at its center, but only when we're outside of it. It makes calculating the orbits of satellites and planets way, way simpler. And this powerful concept of using symmetry to cancel things out, it's the exact same logic behind Gauss's law in electromagnetism. It just goes to show you that sometimes the most powerful tool a physicist has is symmetry. So, we've solved the puzzle for what happens inside the shell. But it opens up another question. What if you're outside the sphere? How does it pull on you then? Well, that's the other half of the shell theorem, and believe me, it's just as cool. Think about that for a while and keep on exploring.